This is lecture 2 of Physics 210A. Thermal physics. And I just recall that in lecture 1, we talked about the work done by a system, describing things in terms of macroscopic variables, and so on. And that kind of forms the system of thermodynamic science. Now, one concept that we need in this is the equation of state. To introduce this, let me recall that in thermodynamics, we find relations between macroscopic quantities and how they change. So, equation of state describes that relationship. For example, you already know that for an ideal gas, we have the pressure times volume equals number of moles or T. Similarly, for a dielectric, where the variables are the polarization P, electric field E, volume V, and there's a property called chi, the electrical susceptibility. So P is written as chi E V, where chi susceptibility could be a function of temperature. Similarly, for a paramagnetic substance, we have the magnetic moment equals some constant C, which is known as Curie constant Cc, divided by T times H, or Cc divided by T B over mu. So, these are the kind of relationships that one has, and these can be used to calculate work done. So, for example, I'm going to ask show that work done in an isothermal quasi-static change of state for a dielectric is given by W equals 1 over 2 V chi P final square minus P initial square. So, the answer is quite simple to get, because I know that dW is the electric field times dP. This we had obtained yesterday. So, this can be written as E chi V dE, and that gives you chi V by 2 E final square minus E initial square, and if you substitute for E in terms of P, it comes out to be 1 over 2 chi V P final square minus P initial square. So, you see how equation of state can be used to calculate the work done. So, when we use thermodynamics, when we apply thermodynamics to different systems, we do need the equation of state. Now, you can see that we're dealing with systems with many variables. So, in giving equation of state, we are expressing one of the macroscopic variables in terms of others. And therefore, we can actually obtain some relationships between them, these different quantities. For example, in a gas, we have a variables P, V, and T. Given a number of moles, then the relationship in general for the equation of state is this. Or we can write P as a function of V and T, or V as a function of P and T, and so on. So, now what we need to do is obtain some relationships using partial differential derivatives and use them to obtain certain relationships between measurable quantities for these systems. So, in general, and I'm referring to 3 variable system. So, I have f x y z equals 0. So, suppose I were to write x as a function of y and z, then I'll have the full derivative dx, an element, as partial x partial y at constant z dy plus partial x partial z at constant y dz. Now, I may want to expand this I may want to expand this, taking z equals z, x, and y. Then I have dz equals partial z, partial x at constant y, dx plus partial z, partial y at constant x, dy. And therefore, I get dx equals partial x, partial y, z, dy plus partial x, partial z time at y, and for dz I substitute partial z, partial x at y, dx plus partial z, partial y at x, dy. Now, if I collect the terms in terms of dx and dy, I get dx equals dx dz y dz dx y dx plus partial x, partial y at z plus partial x, partial z, partial z, partial y. This will be at y, this will be at x, dy. So let me just go over what I did just now. What I did was took dx to be partial x, partial y, constant z, dy plus partial x, partial z at constant y, dz, and then took z to be a function of x and y, writing dz equals partial z, partial x, y, dy plus partial z, partial y, constant x. Sorry, this will be x, dy. Substituted this back in here and got the relationship here. Now, again consider x and y as independent variables. Then the relationship here gives you partial x, partial z at constant y, partial z, partial at constant y is equal to 1, and partial x, partial y at constant z is equal to, because that term in the square bracket is going to be 0, and this is going to be equal to minus partial x, partial z at constant y, partial z, partial y at constant x. Let me call this relationship 1. Let me call this relationship 2. So if I multiply in 2 by dy dx at constant z on both sides, so multiply 2 by dy dx at constant z on both sides, the left hand side gives you 1, and right hand side you get minus partial y, partial x at z, partial x by partial z at y, partial z, partial y at x. That's another relationship. So I've gotten 3 relationships, just simple partial differential relationships, but these are useful in deriving relationships in thermodynamic states. And we'll do that now. So for example, use the relationships derived to connect change in pressure to that in temperature and volume through some properties of the system. Now, we are not going to assume any specific relationship between pressure, volume, and temperature. All we are going to say is that I have pressure as a function of volume and temperature. So I can write dP equals partial P partial T at constant volume dt plus partial P partial V at constant temperature dV. Now, the second quantity dP dV at constant temperature is related to isothermal compressibility of the gas. That's a measurable quantity. That's a property of the system. So how is isothermal compressibility defined? Isothermal compressibility, kappa, is equal to minus 1 over V dV, dP at constant temperature. So if I multiply by dP dV at constant temperature on both sides, I have kappa dP dV at constant temperature equals minus 1 over V, and I get 1. And therefore, dP dV at constant temperature is minus 1 over kappa V. So the second part here is given. Now let's calculate the first part and relate it to some measurable quantities. So I want to find partial P partial T at constant volume, which using the mathematical identity I can write as minus partial P partial V at constant temperature times partial V partial T at constant pressure. And I'm writing it in this particular way because this is related to volume expansion coefficient of the gas. And the first quantity we have already seen is related to compressibility. So I have partial P partial T with respect to V is equal to minus, again, dP dV, we have already calculated, it's minus 1 over kappa V, and then I have dV dt at constant pressure, and that's the compressibility, constant pressure compressibility, which is then plus 1 over V dV dt at constant P is beta divided by kappa. So you've calculated dP dt, and therefore dP, change in pressure of any system, is going to be beta over kappa dt minus 1 over kappa V dV. Beta and kappa could in general be function of temperature. If they are not, then these equations are very easy to integrate. And beta and kappa are measurable quantities. Let us now apply this to a stretched wire. Where the force that you apply on a wire F is going to be given as K L minus L0. That's the equation of state. It's limited to elastic regime, but nonetheless we're going to work in that regime. So force is given as, by this Hooke's law, equals K L minus L0. L0 is the unstretched length. So now, for a stretched wire, we wish to relate how the force changes if you change the temperature of the wire but want to keep its length the same. So what this quantity means, this quantity is telling about the change in force with respect to temperature keeping the length the same. So this is the kind of problem most of you have done in your JEE preparation. So I'm just going to repeat that JEE preparation argument, your 12th grade argument, and then show how it can be easily obtained using the mathematical relationships that we just obtained. So suppose I have a rod fixed between two walls so that its length remains the same. And you increase its temperature. As you increase the temperature, the length is going to increase. So what does one do? This wall applies a force this way so that length goes back to the original one. So that force per unit area is going to be equal to Young's modulus times delta L over L. And I'm going to put a minus sign because it's in the direction towards into the rod. So this is minus y, delta L is alpha, delta T times L divided by L. So this L cancels. So the force divided by delta T, which I'll say is delta F delta T, keeping the length the same, is minus y times area times alpha. This is what you have done in your JEE. Now let's do it through our sophisticated mathematical argument that we just obtained. So partial F partial T at constant length is going to be equal to partial F partial L at constant temperature, partial L partial T at constant force with a minus sign. Let's write it on the next slide. I have partial F over partial T at constant length. This is what I'm after, is partial F over partial L at constant T, partial L over partial T at constant F. Now I know that delta F over area is equal to y delta L over L, and therefore partial at constant temperature. That's the Young's modulus definition. So partial F partial L at constant temperature is equal to A y times divided by L. There's a minus sign here. And therefore, partial F partial T at L is equal to minus A y 1 over L partial T at constant F. But that's the coefficient of linear expansion, alpha. So this is then minus A y alpha. So you immediately get partial F partial T at constant length is equal to minus A y alpha. Earlier we got it through physical argument. Now it's a purely mathematical argument, and we got this. So these are some of the things I wanted to do in this lecture for you, and now I'll leave this lecture by asking you to do a demo related to first law of thermodynamics, a demo. We know that for a stretch wire or rubber band, we have du equals dq plus f dl. Take a rubber band, pull it. So step 1. Take a rubber band and stretch it. And just hold it for some time so that it equilibrates, the temperature is, all equilibrates, and then step 2. let the rubber band come back to its original length quickly. Should be so quick so that the process is adiabatic. That means dq is equal to 0. In this case, it will be roughly 0. So I'm going to have now du equals dw, which is going to be, if you're holding it and let it just come back, so it's going to be equal to f dl. So delta u is going to be f dl integration, which is going to be L large to L small. So this is going to be less than 0. So this implies that u decreases as the rubber band comes back to its original length. And this means usually higher the temperature, higher the internal energy, lower the temperature, lower the internal energy, the rubber band should cool. So step 3. Feel the rubber band on your cheek. That is a very sensitive area, so you can immediately make out any small temperature difference and see if it has indeed cooled down. So with this, I stop this lecture and summarize it. That idea of equation of state has been introduced to, or if you want, 3 mathematical relations have been obtained and applied, and finally a demo for, if you like, adiabatic cooling has been suggested. Thank you.